Hi there, it's been a while since my last video, but this is another video, and I was about to say another short video from KOJRO, but as you probably know by now, I'm not very good at making short videos. But this time we will continue about the C64 power bricks, and not so much the bricks themselves, but we are going to go into why these fail and why this is a bad construction from the start. And if you know everything there is to know about power supplies, then you can just skip this video. But if you want to learn something about normal serious liner regulators, and also in fact something about switching regulators, you might watch this video and learn something. So let's get straight to the point, and we start by doing some measurement on this power supply. We connect this up to a resistive load, and we see how much the power drops when we draw some power from this, to have a good measuring point of what the internal voltage drop of this power supply is. And today we are back in the shed, and I'm looking at how much voltage this power supply can provide when it's loaded, and then I'm thinking the output of the transformer really. So I'm going to connect these wires straight to the output of the transformer, and then I have to use the ground winding here, and I have to use the combined from the rectifier here. So I'm going to connect this like so, and I have connected this to one end of this resistor network, and this is 8.2 ohm resistors that will handle about 2 watts each, and I've connected them 2 and 2 in series, and all the ones like this in parallel afterwards. So the resulting resistance of this is about 4 ohms. So now we are going to measure how much voltage we actually get on the output of this, and I have my matrix here, and I have my scoop meter, and I'm not sure how much it's visible on this input with the light I have here now, so I just have to wiggle it a bit, I think. The scope meter is very difficult to get a good contrast on the display actually. I do have this contrast adjustment here, but I don't think it much of a difference. Yes, anyway, we are going to measure DC volt like so. This one I just pin underneath this one. Like so. And this I will just clamp it in here, I think. And I will just connect this to power like so. And I have a voltage, and this is probably getting hot, and I get about, this was actually quite difficult to read, I have to turn off some light, and I do just get about 7 volt out of this. And I will also do this with a big capacitor here to see how that goes. So I will just take and solder in the capacitor from before, this 2200. It won't be perfect for the ripple that will be on this high power draw, but that won't matter much. And remember, this is loaded now by this resistor network, not the one on here. So I will just take this and I will solder it in. Now you don't have to trust this reading here, because I have desoldered some of the other points here. What really is the point here is that we should measure what's over this capacitor when we load this with this 4 ohm resistor. So I'm just going to connect this again like so, and like this one was a bit more, it was this hook, it's a bit more difficult to fit, but this one will do. And we now have a ripple voltage of about, it's 1 volt ripple on the output. I can really feel this getting hot now. And we have 9.29 volt output when we are having this load. And this load is almost the maximum of what this can handle, I think. We do have 9.3 volts over 4 ohms, and that should be more than 2 amps of total load on this power supply. And I can do a measurement with my Metex, put this in DC volt, and I try to measure just over the resistor network here. And here it states about 9 volt exactly. And this is because there is some leads leading out to this from where we have here, and these thin clamps that I have here, that's not made for this kind of power. But I do have about 9 volt. That means that we have the voltage that we can expect to have on the maximum load of this transformer, and that is about 9 volt output. So the open clamp was about 13, but the maximum draw will be about this. And if I put this in AC, we will just measure the ripple and not the voltage underneath on this. So I put it like so, and you can see that the ripple voltage is about 1.35 volt. Yes, I will just disconnect it before I burn these resistors. This power supply is getting warm, but it's not really hot. To find out how much power is dissipated, we first have to find out how much voltage the transformer can deliver when it's loaded with the maximum current. And that's what we did in the video piece that we showed just before this, and we did find that it drops from an open circuit voltage of about 13 volts rectified and smoothed with a smoothing capacitor to about 9 volt with some ripple with an absolute max draw of the transformer. And we have set the max draw of the transformer where we have anyway reached the power limiting value in the 7805, which is about 2.2 amps. And to accomplish this, we have used 8.2 ohm resistors that we have coupled like so, and this gives out a resulting resistance of about 4.1 ohms. And this is able to handle about 16 watts or so, and this is quite good power resistors, so they can for a short amount of time handle more power draw than this. We can sort of cool them in some water and so on to have them deliver more power, but that's outside of the scope of today's video. What we have been doing here is that we have said that we take the about 9.2 volts and we drops that into the resistors of 4.1 ohms, and we draw about 2.2 amps out of this power supply. And that means when we are going to measure how much voltage actually is dropped over the power regulator, we will use this value, and we will make an assumption about how much is over there. And one thing that's worth to notice is that the transformer is only lukewarm when you draw 2.2 amps out of it. And that means that the real heat source here is the power regulator circuit. And when I say we make some assumptions about the voltage that we have at a given current from the transformer, we say that this is an not ideal transformer, but it's a transformer that it is only limited by the resistance in the copper wire. We see here that we have an open circuit voltage of about 13 volt, and we have the 2.2 amp current draw. We have a voltage about 9 point something volt. That will be the data we take with us into our next calculation. And here we make the assumption that we now have about 1.7 amps, and that is what this circuit actually is rated for. And we say that we have about 10 volt to make this easy on the output of the transformer. That means that we have a difference in voltage here from 10 volt to 5.2 volt, and this voltage is being dropped over the regulator here. And to make these calculations, we only assume that this is a resistor, and we see that it's 4.8 volt with 1.7 amps. that you lose over this. And with the minimal draw, we know that this will be about 13 volts, so you have about 7.8 volts over the regulator when the transformer is almost open circuit, and that is because we have the power that runs into the regulator, and we also have the current from our last video where we have the resistor network of about 103.5 ohms, something that also draws a current. And here we can see with the maximum power load we have 4.8 volts as we calculated here, and we multiply that with 1.708 amps because we take this 8 milliamp current also with us, and we say that this circuit dissipates 8.2 watts when it has the maximum power draw. And that means that half of the wattage, or about half of it, actually get dissipated inside the power regulator and the rest in your Commodore 64. And when this transformer is idling, you don't have anything connected to it, or you have a C64 connected to it but not turned on. It will be this calculation, and this is 7.8 volt, that is the open clamp voltage, minus the 5.2 that you have here. And this is multiplied by the currents, 8 milliamps into this, and 0.052 amps, 52 milliamps. That goes into the resistor network of the 103 ohm resistor that stands to raise the voltage with the 0.2 volts here. And that is about half watt. So this power supply consumes a half watt of power even though nothing is connected. So the internal power dissipation on this power supply is between 0.5 watt and 8.2 watt. And then we had said that this transformer is about idle, and it's not. It's nothing close to that really. It's about 80 to 90% efficient, and that means that you have to raise these values by 15 to 20% something to get the actual power dissipation within this power supply. And something that's also worth to notice is that back in the day, Norway and a lot of other countries in Europe had 220 volt as the mains voltage. But to increase the efficiency of the grid, we actually increased this to 240 volts. And this 240 volts, you can actually have a 10% difference in this. So this could easily mean that this could be maybe in a modern house today, you can have about 250 volts in this. And that's more than a 10% increase in power waste because of the raise of the input voltage. And that has two main factors that we have to take into account, and that is the raised input voltage will increase the current and the heat that goes into the primary winding of the transformer, but it also gives out a 10% higher voltage that needs to be dropped over the power regulator, so our measured values is a bit higher than they was calculated back in the day because of this increase in mains voltage. It's also worth to notice that the old footwarmer power brick has listed here the total transformer capacity with both the internal loss and the external draw, while these newer ones only have listed the output efficiency and not the power that is dissipated internally. We can see that by the calculated value here, that this is the maximum power draw of the 5 volt, and this is the maximum power draw of the 9 volt, and that is about 7.85, so nearly 18 volt amps. It's also worth to notice that the newer power bricks actually has 3 secondary windings, 2 for the 5 volt that is coupled so that you only need 2 diodes to get full bridge rectifying, and 1 winding for the 9 volt AC. And that means that this transformer probably is a bit more efficient than this one. And when we speak about transformer efficiency, it's a lot of things to take into account, and this is a normal iron core transformer. Its efficiency is a bit lower than the one with circular core. And you have iron losses and you have copper losses that you take into account. And the copper losses is almost identical to a resistive load, but the iron losses is a factor that depends on frequency and other stuff, and the higher frequency the loss will be less, but up to a degree, of course. And this means that there is an optimum load for this transformer to reach its peak efficiency. But a normal transformer has an efficiency of about 82, 83 something percent, and up to maybe it crosses into 90, but nothing over that. And this is not the same as we measured in the circuit before with the transformer output voltage, because this is a linear graph, while this will have resulted in something that probably would have gone a bit like so. This is an easy assumption to make, and this will give us good enough calculations and indications of how this circuit works. But this figure only takes into account the copper loss and not the iron loss. But as we are mostly using switch mode power supplies today, this is ancient knowledge that you really don't need to think so much about if you are not going to repurpose this power supply with just a switching mode regulator, which is exactly what we are going to do with this power supply to make it good as new again. I am again back in my shed, and this is as we left it last time. The capacitor is soldered in here, and this measurement lead is in place. But what I'm actually going to do, I'm giving up on this power supply, and I'm not been able to find out if there are more connections here that make this go havoc with the voltage. And what I mean by making havoc with the voltage, I meant the experiment that we did in our last video where it came out about 7 volt instead of the 5.2 that we actually expected from the resistor network and the connections that we knew about inside this epoxy. So what I'm going to do, I'm first going to try with the soldering iron to heat up this aluminium, and then I'm going to see if this heat actually spreads to this one. And I don't have a thermal camera, but I do have this infrared temperature measurement tools from Fluke that I can use to see the trends in this. And then I'm actually going to drill out some of this gunk in here. And that means I'm going to drill into the capacitors, I'm going to drill into the power regulator and all the other components that's in here. And that is to make place for a capacitor about this size and this 5 volt regulator, and this is a switch mode regulator that is set to give out 5 volt, and this is marked as being able to deliver 4 amps about of 5 volts, but I am taking everything Chinese and divide it by 2 when it comes to how much it can deliver, at least continuous. So I'm going to put this inside here and have this act as a 2 amp switch mode regulator. And I can of course make this a bit more shallow. I can take out these contacts and I can make these capacitors lay flat on the board, but I'm going to drill out some of the gunk in here and have this placed on top here, and I'm going to make some place for a capacitor or maybe 2 smaller capacitors. And the only components I really need in here are of course the leads from the transformer. I can't break those, and I can also reuse the diodes that's in here, but if I find out that I'm not able to do that, I will just bend up these wires and I will put new diodes over here somewhere. They only have to be able to deliver about 2 amp each of them, then I will have about 4 amps in total if there is a short circuit in this one. And the voltage regulator and all the other capacitors that's in here, they will just get drilled through when I'm drilled into this gunk here. So that's what I'm going to do today. I'm going to put this away a bit, and I'm going to desolder these leads so I will keep them safe. What I'm doing here is that I desolder the leads that's connected to the DC circuit to the power plug, and I also desolder some of the wires that I've used to fixed this circuit in the past. I won't need any one of them, and I'm going to drill besides them anyway. And I'm also taking away the leads that goes into the diodes to keep the winding safe if I slip the drill and destroys the diodes. I have set the soldering iron to 500 degrees, and that's quite a high temperature for a soldering iron, but I intend to try to heat this aluminium to see what the temperature properties of the gunk and the aluminium that resides inside the gunk will be. Now if I'm able to show you the LCD here, but it's showing now about 21.8 degrees, and I'm now going to start to heat up this aluminium. Just putting the soldering iron into the aluminium. So the aluminium is approaching 30 degrees. I will just keep it there for about a minute. Aluminium is a very good conductor of heat. If I measure here, it's now 32 degrees, and on this side it's 21. Yeah, the point is that I'm going to try to heat this aluminium as good as I can. I'm then going to just measure how much this heat is spreading or if it's cooling down real fast. You must be careful not to melt the plastic on the outer case here, because I was thinking of making a full repair with this regulator inside here and ship this back to Tommy so that he can have this as a functional extra power supply. He has one good power supply that he has ordered. I showed it in a video, but this one he can use as a spare, or if he needs two power supplies. The tip of this soldering iron, it's cooling down quite a bit, but it's about 80 degrees on the hottest, 82 something, and this is because it's heating a lot of aluminium. And this aluminium is a good heat conductor, but the transfer from our tip on the soldering iron and to this aluminium is not very great. And what did I just say? It's of course a good thermal conductivity here, because I'm actually cooling down the tip of the soldering iron from 500 degrees to only about 80. But I will try to make the conduction even better to melt some solder on the tip of the soldering iron. It will of course not stick to the aluminium, but it will give a greater surface to transfer the heat from the tip to the aluminium cooling sheet. And we can see that this is working. The tip is now even cooler than it was before, with a maximum temperature here of about, we are reaching 77, but most of the areas it's about 60 to 70 degrees. And this is actually quite cool, but it's not conducting heat as I was thinking it was, because then the heat will spread better than this is now. And while I've been heating this, it was about 22 degrees. By now it will be about the same over here, but over here it has started to warm a bit. So I will just keep the soldering iron here for a minute longer, and then I will try to move it and see which part of this is getting warm.
5 minutes later.
And what we see here, this soldering iron is 60 watts, and even though if we are only able to transfer a small amount of heat, it's not warming up this in any substantial way. And we can't even melt the plastic with the soldering iron directly just pointing into it. And if I measure here now, I see that it's about 58 degrees at the warmest, but it's cooling down, and it's cooling down fast. And that means that the thermal conductivity of this plastic is rather good. It's actually able to transfer and actually maintain and keep a bit of the heat, absorb it, and then transfer it. So the plastic here is actually doing a good job with keeping the components colder than they would be if they was in open air inside this power supply. And now I'm going to take out as much as I can of this gunk and make space for this PCB and some capacitors inside this plastic filling. And that I will be using my drill press to do. For just this PCB I don't need much space, but I will have to make some space for the capacitors beneath this board.
Later that night.
And here you can see the results after I've drilled out what I could from this. And Of course I could have drilled out more, but it will fit in here anyway, and I do think that I will mount this like so, and then I just put some capacitors in here. And the total capacity of these capacitors, when we had this capacitor in here before, 2200 microfarad, we had about 1.30 something volt of ripple. That means that this regulator probably would be able to handle this just fine. But I will put a bit more capacitor than this in here, so that we can draw the full 2 point something amps out of this without the regulator transferring the ripple to the output. Because this switch mode is suppressing the ripple that is on the input, and it does not need more than about 2 volt more on the input than on the output. So we will be able to deliver about 2.2 amps with this one, but I set a goal to be able to deliver about 3 amps in short amounts of time on this one. So that will be what we actually make with this one. I'm not sure if I have the right capacitors, but I will try to see what I can find. Otherwise I can do a test montage with just one of these capacitors. The real difference between a switch mode power supply and a linear power supply is a bit difficult to grasp if you don't have some basic concepts to hang this on. And one of the things that you have to take into consideration is that a normal transistor that is acting as an analog transistor, there will always be some current running through the transistor, and this will always be dissipated as heat in the transistor. And a normal transistor can act in this area here. This is just an example. It's not representative for the transistor that's in a 7805. So this is just the general concept. But here you can see it's working within this range, and then there will be some power. And this power is determined by the power equation here. It's voltage over the circuit times the current running through the circuit. And this will always be dissipated in the transistor itself. When you come to a switch mode power supply, the transistor that stands in the path of the current is acting as an on-off switch. And that means there is no current running through the circuit when the transistor is off. Of course, there will be some leakage current, but this can be about zero, especially if we're talking about MOSFETs and other modern transistors. So there is no current running through the circuit when the transistor is off, and that means that you have the power equals U, that can be, in our case, 13 volt when there is no current, times 0. 0 heat dissipation in the transistor. When the transistor is on, there is running a massive current through the transistor, but the resulting voltage that's being left to be over the transistor is almost 0. It will of course be a minimum current. If you have an old-fashioned silicium transistor, you will have some voltage drop over the collector-emitter circuit. But on a modern MOSFET, this is approaching 0. Even though if you have 1 volt left over this, it will still be a much less heat dissipated in this. Because if you have our 2.2 amps and you have 1 volt left over the switching transistor, you only have 2.2 watt. Instead of the 8.5 that you had on the linear regulator in the same case. So that is the basic concepts of how this is working and why there is no heat dissipated in the transistor or the regulator itself. But of course this is a great and huge simplification, and we will go into some details about switch mode power supplies in my next slides. The definition of a switch mode power supply is a power supply that uses semiconductor switching on-off techniques rather than linear methods to provide the desired output voltage. What we was looking into in my last picture. And the basic switching converter consists of a power switching stage and a control circuit. And the control circuit is a very important part of this. The major advantage of a switch mode power supply is that it's much higher efficiency. And there is much less heat dissipated in the switching transistor, as we have seen. As we also see here, it's more common now that we use MOSFETs because they have a much lower voltage drop when they are in their on state, and they also have a very good approaching zero leakage current when they are off. So that means that when the switching transistor is fully on, the voltage drop across it is basically zero. And when the transistor is fully off, there is no current flow through it. That's the simple way to explain why there is no heat and why the switch mode power supply is so much more efficient. So the transistor is acting like a close to ideal on-off switch instead of almost an analog counterpart that stands in a good old-fashioned analog amplifier circuit. Linear regulators only offer step-down voltage regulation. That's an important fact, and while switch mode power supply can provide both step-down or step-up, we are only going to concern ourselves what's called a buck regulator, and that's a step-down circuit. We also have boost circuits, but we are not going to talk about them in this video at least. And this is my simple sketch, maybe not the most educational picture, but I will try to walk you through this. This is the series transistor, that is the switch that switches on and off. And this has a controller circuit to turn the transistor on off, and it's turned off by applying some kind of square pulse to the gate or basis or what kind of transistor is used. And this control circuit is regulating the circuit, the waveform here, with a feedback from the output. This feedback can be just an electrical feedback, it can be done through a transformer, it can be done through an optocoupler or other means in more advanced switch mode power supplies. The basic concept here is that you have one inductor that's in series with the output, you have one diode, and you have one capacitor. When the transistor is in its on state, it will run the current through this inductor, and the inductor will charge and get a field surrounding it, and the capacitor will charge and reach the common voltage of this point. When this transistor turns off, the field on the inductor will reverse, and we will discharge the drossel through the diode, and the capacitor will try to keep the voltage up here. So that's the simple explanation of this, and the load is of course cut through in parallel here with the circuit. The switching characteristics of this is that the on time of this transistor and the off time, the mean value of this equals the voltage out. And we have taken another example here in the bottom. If the T on time is shorter and the T off time is longer within the same frequency, you will see that you will have a lower voltage out down here. And in fact, we have a formula, a simplified one, that says that the voltage out is the time on divided by the time on added to the time off times the voltage in. And that is what you can see here in this curve also. And when this is detecting that the voltage is rising here, it gives feedback which has this control circuit to make these shorter if the voltage is too high, and it makes them longer here if the voltage is too low. And this is done via some kilohertz, up to 200-300 kilohertz is not unheard of. That means that this is a really fast circuit, and it will compensate the voltage real fast if there is some added or reduced load on the circuit. So what's basically changing is that this edge of the pulse is changing like this to make the voltage out here appear stable to the load. So that's the basic concepts of a switch mode power supply. And we won't go any more in depth in this here, but I think this is an explanation that is understandable to everyone. Yeah, now we're going to see what we can do to rebuild this power supply with a switch mode inwards. And I've chosen to use these high quality capacitors. These are 105 degrees and they're 50 volt and they're 2000 microfarads. And as we was measuring with this one, a 2200 microfarad capacitor was giving 1.35 volt ripple voltage when the load on this was about 2.2 amps. So with 4000 microfarads of capacitors here, we have one risk that we are taking, and that is these diodes will have a much higher start-up current than they would have had with a load like this. But I've been seeing all kinds of figures on this, and this capacitor that's inside this, someplace it's stated 2000 micros, sometimes it's stated that is 3300, and some has even said that this capacitor was 4700 micros. So I'm not sure what to do, but I was thinking I was going to place both this one. I might have to do some more digging. Or maybe I just can fit one of these and maybe I go find one that is smaller, but then I would have to choose a capacitor with a different quality. So I might have to see, I might have to go out in the shed and do some more drilling. Of course there is other ways to make this fit, but I will have to see what's possible within our limits here. It's actually so that even one of these will be difficult to fit without doing some more removal work on this epoxy. And now you can see again how hard this stuff is. If I try with a small chisel, it's breaking like it's really hard and brittle stuff. And it's these really sharp edges on what you're taking, so this is almost like a ceramic material. But I will go out and I will take out some more of this plastic to make at least one of these fit. Yeah, now I have done a bit more drilling and some cutting and taking out some of this gunk in here. Still some dust in here, but I will blow this clean later. And now it is actually possible to fit these capacitors down here, and I can even make two of them fit down in this space, and I will still have space to put this board like so. I have to insulate something to get that in place, but it's possible. So that is how this will be mounted. I will just try to make these capacitor leads as short as possible. Yeah, there is now plenty of space for the capacitors, and I ought to make sure that the leads are as short as possible, and the ground lead will be this common point for the two windings, and the plus will be the common point I have to connect for these two diodes. And both the capacitors of course has to be connected in parallel. And to show you how this works, we have this circuit here where you have these two diodes. They connected to each to one winding, and you have the anode side of the diode connected there, and you have the cathode this way. So if you take the matrix here and do a diode test, yeah, they are both testing fine, and here we see what side is the cathode and the anode, so we know what sides to connect together and what sides to connect to the winding. So that means there will be one lead here, and to this point, and one lead here to this point, and that point will again go up to these here. The problem with using these screw-on clamps is that the leads will be very close here to the aluminium. I don't want that, so I will desolder this, and this other one. Probably I can get away with, I can probably get away with not desoldering that one, but I will do that. Yeah, I just start with soldering the capacitors together and fastening both the ground and the plus wire to the capacitors, and this will be routed through the common winding on the minus side and then to the switch mode board, and for the other it's going to be from the two diodes and to the plus side of the switch mode board. If these leads seem a bit long, it doesn't matter that much because you have this small cap here of 100 microfarad on the input, and you actually have a 1000 microfarads on the output, so it doesn't matter that much if there is some kind of length on these leads, but of course the shorter the better. I have bent the diodes so that they will be able to reach onto the copper from the windings, so that I just solder on, and then it's just to keep this as solid as possible. Yeah, I will just take and desolder these screw-on terminals at a breathtaking speed. By sheer coincidence, the holes that is left from the screw terminals is just exactly the right size to solder in the leads to. I didn't have any red wire for the positive side, but yellow is appropriate anyway because it's not regulated, so it's not 5 volt, and the lead is kept in one length. It's just wrapped around the soldering pads of the different components, the diodes especially, so it's in one piece so it won't break. As we remove the solder pads also on the output, we have to solder the leads from the power cable directly onto the board, but they are also of a similar thickness, so they should go right into the holes. Here I have to do a bit of extra heating because the ground plane on this PCB is rather large, so it has a lot of cooling from the tip of the soldering iron. Now it is a bit of fiddling with wires because this wire that goes to the C64 is rather thick, and we also have to connect the AC wires that we also disconnected to this cable, and they should be connected direct to the terminals on the transformer. Now it is about fixing the board inside this so it won't touch the aluminium and that it will be kept safe inside here. And I do have a slight idea of how I should do that. What I have mixed up here is not epoxy, but it's fiberglass filler with fine-grained glass fiber fillings. And this dries real fast and it gets real strong and it will keep the board safe, and it's also a non-conductive material. Yes, and I know it's ugly, but it's convenient and it's actually the cheapest way, so I do think we are following up in good Commodore tradition here. This will dry in less than 5 minutes, but I'm going to keep this rubber hammer on top of it to keep it down while it's drying.
5 minutes later.
Before we give this a test, we have to solder in the power mains leads, but as we have just desoldered them, it's just to connect them back on the soldering terminals. The lid fits straight back on, but of course it won't be fastened by the original fastenings because they was glued into the epoxy. And we won't fasten this lid yet. We do have to test this power supply and make sure that it works. And this is actually rather disappointing because it now shows 4.8 volts, and while that is sufficient to power your C64, I would have been glad that this was closer to 5 volt, because with the power drop in the lead this will be close to 4.60 something inside your C64 with some power draw. And after we loaded this down with the internal load of the power supply tester, it stayed on 4.75 volt, but we will check that with the Metex. and it showed just 4.78 something on the power rail, and over the resistors where there are some thinner lead attached it was a bit lower. Now I will just connect this to a C64, and this is a C64C with the longboard, so that we can make sure that we test this power supply in proper conditions, and I will leave it on for several hours to see what the temperature of the brick will be. And as we can probably imagine, the power brick now will run quite cool. And on the transformer side it's about 24 degrees at the hottest, and on the other side it's about 21.
Later that night.
And as we can see, there has been no rise in temperature over several hours here, but it's quite cool in the shed today, so it's about, I think, 18 degrees or something, so there is a slight heating in this transformer, but nothing much. And this is where we leave the C64 power brick for this time. We have had some rather long and winding videos about it, and we have gone somewhat into depth on this, but there still are some issues to cover, and we have really not touched into this one yet, so we might have to revisit the C64 power supplies in the future. But for now, I have about, what should I say, exhausted the material that I had on the power brick, so I will need to collect some more. And also I'm leaving now for 3 weeks of summer holiday, so this will put an temporary stop in my videos. I might post one more during these 3 weeks if I get the footage ready. So until next time, and this will probably be the first week in August, I wish you a happy summer holiday. Hope you like the contents. Please like and subscribe, that will make me very happy. And see you, and thanks for watching.